Hi everyone, I'm Greg Stitt from the University of Florida, and in this talk I'll be giving an overview of my lab's new Elastic IP technology that makes FPGAs easier to program by enabling automatic discovery of IP optimizations for different, very individualized use cases. Since this is a brand new project, I'll be focusing on the benefits of the Elastic IP as opposed to how it works, which I'll discuss in a future video. The real intent here is to highlight the advantages to identify potential collaborators, so if you see potential uses for the technology, please contact me at the email address shown. We're open to any form of collaboration, but just to give you a few hypothetical examples, we could evaluate Elastic IP in an existing application of interest to show the benefits, or we could develop new Elastic IP cores to support some new application. So the problem we're addressing with Elastic IP is the fact that optimizing RTL code for emerging FPGAs is rapidly increasing in difficulty. If you've ever used an FPGA, I'm sure you realize they have always been challenging to use, but these challenges are now a prohibitive barrier to using the newest FPGAs effectively. As a result, realizable performance is often far below potential performance, which may cause FPGAs to be avoided in favor of a technology that is easier to use. Now, the main reason for this difficulty is that FPGA designs have an enormous design space consisting of millions of combinations of design and optimization options. For example, different instances of the same module might require different optimizations based on their placement on the FPGA, due to the existence of different resources in those locations. Similarly, a designer must consider what types and how many resources to allocate to each module, which isn't trivial for a complex application. And once that has been decided, you then have to figure out how much pipelining to apply to each module. And although that seems like an easy step, counterintuitively, too much pipelining can actually decrease clock frequencies by resulting in routing congestion that outweighs the benefits of shorter logic delays. And figuring out how to avoid or minimize this routing congestion then requires a ton of exploration into different fan-out strategies and different techniques to reduce resources. So ultimately, the combination of all these challenges make it only feasible for a designer to explore a tiny subset of the possible options. And this problem is worsened by the fact that compilation can take hours or even days for newer FPGAs. So how do designers currently handle these challenges? Well, first, they use IP libraries as much as possible to leverage existing optimized solutions. So they basically search through existing libraries to find cores they need. They then select a specific trade-off from the configuration options for that core. Then, for any functionality not implemented by the IP libraries, designers will then implement and optimize custom RTL, initially making guesses at the design options. Now, unfortunately, there are two significant problems with this approach. First, as discussed on the previous slide, manual RTL optimizations require numerous iterations of design space exploration, which simply isn't feasible due to the lengthy compile times. Second, different use cases often require wildly different trade-offs between performance, power, and resource constraints. And this is a problem because most IP cores have a small set of trade-offs that aren't well suited to all use cases. Or, alternatively, an IP core might have numerous configuration options, which just further complicates the exploration that must be done. So our proposed solution to these problems is to automatically discover use case specific optimizations with what we call Elastic IP. So with Elastic IP, each core has a knowledge base of different implementations that get combined with a design space explorer that leverages this knowledge base to discover new implementations with requested trade-offs and constraints. Now this slide shows how the design process changes when using Elastic IP. The main flow is largely similar, but with a key difference. So instead of selecting from a set of provided IP trade-offs, with Elastic IP, you request an IP implementation with specific constraints and optimization goals. For example, you could say, Give me a 2D convolution core that supports kernels up to 7 by 7, has a clock frequency over 300 megahertz, generates an output every other cycle, and uses less than 5% of the embedded memory. So you can basically request a very specific combination of constraints and optimization goals. Now, after requesting IP implementations for available cores, the designer still has to implement RTL for remaining modules, just like they did before. But now, by making small changes to that RTL code to make those modules Elastic compliant, much of the design space exploration can now become automatic. So there's some huge advantages to this approach. First, it significantly reduces design iterations through automation. Second, it optimizes based on exact goals and constraints. So even when existing IP libraries have a core that meets constraints, it can likely be optimized further for the specific use case. And Elastic IP enables that optimization. Another advantage that we'll see coming up is that Elastic IP is able to discover counterintuitive, low-level optimizations that a designer is highly unlikely to realize. And ultimately, really the biggest advantage is that Elastic IP will provide better solutions in less time. All right, so now I'm going to give you a quick look at how Elastic IP cores work. Unlike traditional IP, Elastic IP consists of multiple implementations that we categorize into bases and transformations. To explain these concepts, I'll use a simple but useful example of a delay module that delays a width bit signal by a specified number of cycles. Bases are essentially different fundamental implementations for an IP core, which are similar to the configuration options in existing IP libraries. So for the delay example, you could have a base that implements the delay solely using flip-flops, which is pretty standard. Alternatively, you could use embedded memory resources such as M20Ks or MLabs if you're on Intel, or on Xilinx devices you could have block RAM, things like that, combined with counting resources as kind of shown in the middle and right-hand side of the slide. Now, each one of these bases provides different trade-offs that are appropriate for different use cases. So while bases are useful by themselves, the real benefits of Elastic IP come from transformations, which are essentially rules that enable the massive automatic exploration. Basically, transformations define an IP core recursively and possibly in terms of other Elastic IP, but really the divide and conquer strategy enabled by the recursion is the key enabling feature. So for this delay example, we can recursively implement a given delay, shown on the left, with two smaller delays, either by splitting the delay based on width, as shown in the middle, or alternatively, splitting it based on depth, as shown in the right, where you're basically dividing up the number of cycles. So although these transformations are conceptually simple, they open up a huge amount of exploration options, where the Elastic IP framework will automatically combine the transformations and the bases to create new implementations. So let's look at some simple examples for the delay. And let's say we need to delay a 40-bit signal by 513 cycles on an ARIA 10 FPGA. Now initially, the Explorer would evaluate the base implementations, such as the flip-flop implementation shown on the left, which is a pretty standard delay implementation. However, this particular implementation, because of its size, requires over 20,000 flip-flops, which is likely not a desirable trade-off for the vast majority of use cases. So for larger delays, such as the one we're working with, the Explorer could also select a base implementation consisting of M20K RAM blocks, as shown in the middle. So although each M20K perfectly supports the requested width of 40 bits, the maximum depth of an M20K is 512 words, so to provide a 513 cycle delay, Synthesis would need to allocate 2 of these, which yields a very poor utilization of RAM bits of just over 50%. So for any use case where you need to reserve RAM bits for other purposes, this particular implementation is going to be very problematic. So really the left and middle implementations aren't that interesting, and they really represent what already currently gets allocated by synthesis tools when you create a delay. So it's the implementation on the right that starts to show where Elastic IP provides advantages. Now in this rightmost example, the Design Space Explorer would apply the depth splitting transformation to create one delay of 512 cycles and a second delay of 1 cycle. Now for this 512 cycle delay, the Explorer would map it perfectly onto an M20K base to get 100% utilization of the RAM bits, while using 40 extra flip-flops to implement the 1 extra cycle of delay. Now on this slide, we have another delay example for a width of 20 bits and for 64 cycles. In this case, the Elastic IP expiration would again find a base implementation using an M20K, but in this case, it would use a single M20K configured to provide 1024 by 20 bits as shown on the left. Now, the obvious limitation or drawback of this implementation is that only 64 of the 1024 RAM words are used, which has a poor utilization of just 6%. Now, alternatively, the expiration could apply the depth splitting transformation to basically create 2 subdelays while matching or mapping each subdelay onto an MLab implementation as shown in the second example. Now these MLabs provide 32 by 20 bits each, which provides a perfect utilization of the RAM bits for this delay instance. Alternatively, the expiration would also find an implementation of 1280 flip-flops, which might be desirable when you want to reserve all RAM resources for something else. Or as shown on the right, the expiration could find a point in between where it applies this depth splitting transformation to create 2 subdelays, but uses 1 MLab for one of the subdelays and 640 flip-flops for the other subdelay just to provide another trade-off. And finally, here we have a similar example for a delay that requires a width of 21 instead of 20 bits. So we're just adding 1 bit to the width. So in this case, the Explorer could again find the M20K solution that again wastes a large amount of memory. Alternatively, we start to see slightly more complex solutions now, with the Explorer applying both the depth splitting and width splitting transformation. For example, the second instance shown on the slide, here we have 2 MLabs that provide an effective way of delaying 20 bits, with the 21st bit being delayed with flip-flops. Or, again, we could use all flip-flops, or we could use a different mix of MLabs and flip-flops, or we could use all MLabs, 4 separate MLabs in this case, with just a lower utilization of bits in order to save flip-flops. The key point here is that none of these implementations are better than the others. They just provide a set of trade-offs that are attractive for different use cases. For example, even the M20K implementation, if your application isn't using any M20Ks and you don't need them for anything else, then the leftmost example is likely an attractive option despite the low utilization. So the primary advantage of Elastic IP is that it enables the automatic discovery of an attractive trade-off for a use case based on the requested set of constraints and optimization goals. Now, if we compare this with what current synthesis tools do, at least from what I've seen, they tend to use a single type of resource for a delay, either a set of flip-flops or some embedded memory resource, which is not attractive for all use cases. And of course, a designer could manually perform all of these low-level optimizations that I've demonstrated through Elastic IP, but that requires a significant effort to identify the appropriate resource mix. You basically have to manually do the exploration that is being done by Elastic IP. It requires more effort to implement it, and even if a designer is willing to do that for a given delay instance, it quickly becomes impractical when you have a lot of delay instances in an application. On this slide, we illustrate how this exploration integrates with a typical RTL design process. So first, a designer requests the constraints and goals for the IP, in this case a delay instance. The Elastic Design Space Explorer will then identify an appropriate implementation for that request. It will create the corresponding design hierarchy that implements that implementation, and it will convert that design hierarchy into a configuration string that gets passed as a parameter to the corresponding delay instance. So in this example here, we show it using VHDL generics, but it would work the same way with Verilog using parameters. You basically have a configuration string that will configure the internals of your delay instance or whatever your Elastic IP is to function based on the implementation that was selected. So now we're going to look at a more interesting example of a multiply add Elastic IP core, which multiplies n pairs of inputs and adds those products to produce a single output. So this is a very common operation in DSP and machine learning. So for this IP core, we show two potential bases. The first is just a single multiply for the case of a single pair of inputs. The second base is similar and provides an implementation that multiplies and adds two pairs of inputs. So each of these bases has optional pipeline registers, which adds some additional amount of exploration that can be done. For the transformations, we show two possible options on this slide. One is a standard multiply accumulate tree architecture where you first multiply all the pairs of inputs and then use an adder tree to add all the products. So this adder tree would itself be another Elastic IP core with its own exploration options that I won't discuss, but hopefully you can see some of the possibilities there. Now this second transformation is a little counterintuitive, but I'll show soon that it enables important low-level optimizations. So this transformation first recursively instantiates a smaller Elastic multiply add that uses n-1 inputs, and then includes an extra multiplication and adder to produce the final output. But to ensure the final multiplication arrives at the right time, the transformation includes delays that delays the inputs to the multiplier to ensure that they align with the output of the recursive multiply add. Now, while this transformation is conceptually simple, it's not obvious why it's beneficial. In fact, in most cases, this would generally be a bad design. So first of all, it will generally have a longer latency than the first transformation that uses the adder tree. And second, it requires two delays that weren't needed in the other transformation. And even those delays are counterintuitive, since it would seem to make more sense to perform the multiplication and then delay the product, which would require just one delay instead of two. However, we will see on the next slide why this specific non-obvious transformation has huge advantages. So this slide illustrates three of many possible implementations that will be discovered during exploration. For this example, we target 32-bit floating point on an ARIA 10, where each operation is already pipelined, so we omit any registers in the figures. Now the leftmost example is the standard way of implementing a multiply add. The advantage of this implementation is that each node maps to a single ARIA 10 DSP unit, so it only requires DSP resources and leaves everything else free. However, there are some significant disadvantages. First, it requires 2 to the n minus 1 DSPs, which could be a problem for large values of n. Second, the DSPs are connected over the reconfigurable interconnect, as is usually done on an FPGA, which likely slows down the clock because that interconnect adds significant propagation delays. The middle of the slide shows a less obvious implementation discovered by the exploration. So this example leverages the counterintuitive transformation shown on the previous slide to create a sequence of adds with increasingly delayed multiplies preceding those adds. Now, it is highly unlikely that any designer would knowingly implement a multiply add this way without low-level knowledge of the ARIA 10 because of the extra latency and the extra delays. However, the reason this is beneficial is that the ARIA 10 DSPs have the capability of performing both a multiplication and an add in the same DSP resource but only when chained together in this type of sequence, which requires the extra delays. Now, the huge advantage of this implementation is that it uses n DSPs instead of 2 times n minus 1, which is almost a 2x improvement. In addition, this chaining feature uses hardened interconnect between the DSPs that skips the reconfigurable interconnect, resulting in faster clocks. One obvious disadvantage is the increased latency. However, latency is not a problem for many pipelines, and the increase is likely to be negligible compared to other sources of latency, at least for certain situations. A more significant disadvantage is the need for 2 times n minus 4 delay instances, where the depth of each delay increases with n, which creates a potential RAM resource bottleneck for large values of n. However, Elastic IP exploration can solve this problem by combining the transformations during exploration. As shown on the right, the explorer can apply the counterintuitive transformation to find sub-solutions that do not have a significant RAM overhead. The exploration can then use the first transformation to replicate those instances and follow them with an adder tree to create a trade-off between the two other extremes. This now allows for a non-obvious way to create more effective solutions for large values of n. Now, the rightmost implementation does leverage an adder tree, which would use 1 DSP per add, but by extending the Elastic IP exploration to the adder tree itself, the explorer could start to use lookup tables for portions of the adder tree after it had exhausted DSP resources. And as you can imagine, there are numerous other trade-offs that can also be discovered. Most importantly, none of these are inherently better than the others. They are each attractive for a specific use case, which Elastic IP discovers automatically. Since that was a lot to take in, I want to summarize the advantages that we just saw, in addition to other advantages. So first, Elastic IP is able to automatically optimize for different input sizes. It is also able to automatically optimize for different data types. So we just saw examples of floating point implementations, but if we were to look at integer or fixed point, we would likely see significantly different implementations discovered during exploration, which is important because different resource types on different FPGAs require different types of optimizations. Similarly, Elastic IP is able to automatically adapt to different DSP resources on different FPGAs. So Xilinx has different types of DSP resources. So does Intel. So the Aria and Stratix 10 have a DSP that is different than the Max 10 DSP. So each one of these DSPs provides different resource combinations with different latencies. Each requires different optimizations. You could potentially manually optimize for each one of these resources, but that requires low-level knowledge of each FPGA, and that manual optimization is not ideal anyways because it reduces the portability of the code. With Elastic IP, it will automatically optimize for the underlying DSP without you having to do anything special in your high-level code. Another advantage is that Elastic IP can automatically use multiple types of FPGA resources. And we saw an example of this where with the adder tree, it might use DSPs initially, and then after exhausting those DSPs, it could switch to lookup tables to implement the remaining adds. What's interesting is we don't actually need a complex example to show significant benefits of Elastic IP. Quite possibly the simplest logic component we can consider is an AND gate, which we show still has significant benefits when implemented as Elastic IP. The potential problem with AND gates, or with any reduction circuit, is that wide gates create a path through multiple lookup tables before reaching a register, which is a potential timing closure bottleneck. So here we will show how Elastic IP can automatically optimize such logic for any targeted FPGA regardless of the LUT structure. For this example Elastic AND gate, we use a single base that ANDs n bits together with an optional flip-flop on the output. Now this base applies as long as n is less than a separate parameter b, which basically defines the maximum base inputs for an AND instance. Now, for this example, we use a single transformation. You could have more, but in this case, we're just going to use a single transformation that divides up an N-bit AND gate into a group of smaller B-bit AND gates, which are then followed by a smaller recursive elastic AND. Now on this slide, we see some huge advantages from this simple transformation and base. So let's say here our goal is to maximize the clock frequency without a latency constraint. In this case, Exploration will discover that by setting the B parameter equal to the number of LUT inputs for the targeted FPGA, it will result in a pipeline design where the maximum delay between registers is always one lookup table. Now this is a huge optimization because it means that the logic delay is now constant for any number of inputs. So a 4-bit AND and a 64-bit AND will have the same delay between registers. Of course, a designer could do this optimization manually, but that would be very tedious, especially since it would change for every AND instance and for every targeted FPGA. With Elastic IP, the designer simply instantiates an Elastic AND, and the Exploration finds this efficient solution. In addition, the Explorer could have optimized for other constraints or other goals, which is really where the benefits of Elastic IP come in. You simply request an implementation for your use case by specifying constraints and goals, and Elastic IP discovers a specialized implementation. In summary, I showed that a thorough optimization of applications for emerging FPGAs is quickly becoming infeasible due to a huge design space and lengthy compile times. It also requires low-level knowledge of each individual FPGA, which most designers don't have. And on top of that, the optimizations reduce the portability of your code, which is not ideal. Now, we proposed Elastic IP as the solution to this, where Elastic IP allows designers to request a specific implementation for an IP core based on a specific use case. And we showed that this enables automatic optimization for different input sizes, different data types, different constraints and optimization goals, and different resource mixes within the FPGA. Now in this talk, I mainly focused on what the benefits were of Elastic IP. I will have a future presentation that explains how all of this Elastic IP exploration works. But if you are interested in collaborating with us on this project, please send me an email at the address shown on the slide, and thank you for listening.